So, now we will look into the calorimetric signal. What do we get from calorimeter? Yesterday, when we talked about the thermodynamics, we saw that okay, this you can get the enthalpy. So, whatever heat the measurement you get can relate to enthalpy of a reaction, right. So, the signal what we get is the power as function of time. So, keep in mind you have this for isothermal calorimeter for an example, right, this kind of plot, right, you get this power output. So, the signal is power as the function of time is measure of the rate of reaction. Now, we will see how can we use that signal to know more about the kinetics. Kinetics means how fast reaction is going, right. We are interested in the rate because that is very important. Two different reactions at different temperatures, right, will have different rates, right. So, it is very important to know the rate of reaction. So, let us see what is it. So, we are saying dq over dt, let us say this is we are getting this power, right, dq, q is heat. So, it is easier to understand, it is like a joule per second, understand, power, right, that is what you are getting, that is the output dq over dt. Whatever power you are getting is because of some reaction, right, you can relate it to dx over dt. Dx over dt is the rate of increase of the amount reacted. Obviously, right, you start with 0% when nothing has reacted. Now, if you monitor that, dx by dt will give you the rate of increase of the amount dx, right, and associated enthalpy change. Enthalpy change, so again dx over dt, right, this is gram over second for an example, times delta H again is joule over second, right, it is clear. So, sorry, joule over grams, right, delta H is like your heat over joule per gram. So, is this clear? So, dq over dt is the power signal, power heat rate equals to enthalpy, this rate of increase times delta H, it is clear, right. Okay. Now, if you integrate it, what you get, the integral of power with respect to time will give us the cumulative enthalpy. So, you have this P over T, P is nothing but joule per second. If you integrate over time, you will get joule total enthalpy, right. So, Q, the Q is the enthalpy is equals to X times delta H, right. X is the amount of material that has reacted, right. When X is 0, Q is 0. When X is 100%, your Q is equal to delta H. It is clear? Okay. So, now let us look at the simple reaction where you get, suppose A gives you B and there is a single mechanism, right. Some reaction we are talking about, it could be complicated also, it could be A plus B equals to C, it could be A plus B equals to C plus D. This rate of reaction can be related to the amount of A that has reacted simply. So, what you are saying, so you start with A, now after X, after some time what happened, part of X has reacted. So, now you have A minus X and B is X. So, we are measuring this change in this amount X. So, dx by dt is the rate of reaction, okay. A equals to, it is proportional to, right, that is just coefficient you get later, it is proportional to this. Just pay attention to A minus X because that matters how much is left, right, and this n is to the power n means n is the order of the reaction, okay. And then that is a proportional, like rate is proportional to this, then if you get this coefficient like reaction rate constant. Remember you have V here, it is because we are using X in amount. X we are talking about in grams. Lot of times you will not see this V because V terms gets dropped because you are talking about the concentration. If you talk about X like concentration, that means mass per volume, right. So, then you will not see this V term, but here since we are talking about amount, you have this V term, nothing, it is okay, but it is basically same expression, okay. So, now you have this relation where you can relate this reaction rate to the amount. Now, what we can do after substituting for dx by dt, now we know in the last slide dq over dt equals to dx dt times delta H, right, that we know. Now we can calculate dq over dt, that is the signal we are getting from calorimeter. dq over dt is joule per second power. Now dx by dt, you replace it, you get this term, k times delta H times volume is the volume of reaction volume to the power 1 minus n times A minus Q over delta H. It is nothing but substitution, right. So notice what you have, you know P, right, and we know P with the time, right, and N is the reaction order, delta H is enthalpy, K is the rate. So now suppose you have this power at different time, basically you can get a relationship between Q and what you say function of time, right, it will be a function of time, and also you will have some terms, right, because you can integrate this, right, you can write dq equals to this times dt, right, then you have a term q as a function of time. Now you have this data point, the point is now you know how much q you are getting, what is the heat at different time intervals, so you can plot it, right, you can plot q versus t, something like, could be something like this. Now the idea is you can use any technique, any modeling, any optimization to get these parameters n, k, delta H, right, you know the value of q at different time intervals. Now it is just matter of getting this n, k and delta H, that tells you about the reaction. N is the order, reaction order, you can tell whether it is 0 order reaction, first order reaction, second order reaction, k is the reaction rate, how fast the reaction is proceeding, right, and delta H is the enthalpy, right. So just from calorimetry, like in this case we saw from isothermal calorimetry, we can calculate these thermodynamic and kinetic parameters. For this obviously you need data, right, first you have to collect the data, then you can use this data to get the values. Is it clear? Okay. Now we will look into some application. It is very important to now look into the applications of calorimetry. The focus will be more on isothermal calorimetry because that is used quite a bit. I will also draw some applications from adiabatic calorimetry where, you know, so that you can see the similarity, okay. But most of the time we will talk about isothermal calorimetry because most commonly used technique these days. So where we can use, right, this is lot of advantages. We can determine the heat of hydration of a reaction, right, heat of hydration at different temperatures, okay, because we can maintain the temperature, we can change the temperature. So we will know the heat of hydration at different temperature. If you do that, you can also calculate the activation energy, because when you have a data at different temperatures, you know that you can calculate the activation energy. I will look into the method we can use to calculate the activation energy, and tomorrow I will also talk about the homework assignment which will be based on the calculation of activation energy. Influence of temperature on hydration kinetics, it is very important, you know, suppose a reaction is taking place at really low temperature, 5 degrees Celsius, is different than the reaction taking place at 30 degrees Celsius, right. So we want to understand how the temperature influences the kinetics, right. Also we can use it to understand the influence of water cement ratio. Simple example, right, you have 3-4 low water cement ratio, high water cement ratio, you can use this technique to just see the effect of that. Sulfate optimization, you must have heard of it. It is nothing but optimization of gypsum. See, to make cement, eventually what you do, you grind clinker with gypsum. How do you determine how much gypsum you have to add? Conventionally what we have been doing is we optimize the strength, right. You add 1%, 2%, 3%, 4%, 5% of gypsum, then you calculate, you determine the strength and see where you are getting the maximum strength. Usually it is around 3 to 5% typically, that number you should know. But you can also use calorimetry, isothermal calorimetry to get the optimum sulfate content. So, you can see it is also non-destructive technique. We do not have to do a destructive test. You are making non-destructive measurements. Reactivity of supplementary materials, very important. These days we are using lot of materials, new materials, right? Pozzolanic materials, supplementary cementitious materials, slag, fly ash, silica fume, metakaolin, calcined clay. How do you understand or examine the effect of these materials on the reactivity of system, right? So, this technique can be used to understand that. Also important is cement admixture interaction. Admixture, right? We are talking about, suppose, chemical admixture. We are using retarders, we are using accelerators, we are using superplasticizers, various admixtures, chemical admixture. There is no concrete which does not have any chemical admixture, right, these days. When we are talking about high strength concrete, high performance concrete, right, we are always using some sort of admixture, chemical admixture. So, we want to understand the effect of that admixture. What we are interested in, understanding the cement admixture interaction. If you use particular admixture, does it delay your setting? Does it accelerate your setting? Right? What is the influence on the main heat, main hydration? These things we want to understand. So, this technique can be used to examine those interactions. Okay. So, starting with determination of heat of hydration. Simply what you do, you prepare your sample, and in case of here the plot, you compare 3 different techniques actually: isothermal calorimetry, semi-adiabatic, and heat of solution. Okay. So, you notice that first of all the heat of hydration from semi-adiabatic is higher than isothermal calorimetry, right. It is again because of that temperature effect, right, because when you are increasing the temperature, you influence the cement hydration also, right. So, these are the things you have to keep in mind. Roughly this number you should remember, you get 250 to 300 joule per gram, right, that is the heat of hydration for the cement, right. Obviously that will change depending on the temperature, depending on what is meant, but that is a number good to remember, right. And the heat of solution, basically heat of solution is nothing but you are dissolving, as I explained, your samples in very strong chemicals like hydrofluoric acid, nitric acid, right, and then you are measuring the heat of hydration, right. Because you have to use these hazardous chemicals, not many people use this heat of solution, because it is you have to deal with hydrofluoric acid, which is very hazardous. So, but anyway, the values you get are very consistent, right, very similar to what you get from isothermal calorimetry. Okay. Semi-adiabatic heat of hydration is usually higher than isothermal heat of hydration. Now you know why. Okay. So, idea is you should appreciate the difference. We cannot just compare, right, we cannot just compare, like, so you have to always know the conditions. You can't, like someone says I determine heat of hydration and found it to be 350, someone says 200, you have to always ask how did you calculate, okay. Then they say okay, we use the semi-adiabatic calorimetry, makes sense, that is the point, right. But see, you are able to capture the cement hydration, okay. Okay. Second thing, we also can use this technique to estimate activation energy, okay, activation energy. See, this small review already you are familiar with, suppose Arrhenius equation. What do we mean? See, the reaction rate is dependent on the temperature. So, Arrhenius relationship basically is used to describe this relationship. K is the rate of reaction, or in this case you can say rate of heat evaluation, it is dependent on the temperature using this, right. It is a standard relation you use. Here you see EA is the activation energy, R is ideal gas constant, T is the temperature, K, right. This is the relationship between the temperature and reaction rate. Second thing what we see, okay, now suppose you have concretes, for an example, at 2 different temperatures. One concrete is at 15 degrees Celsius, one concrete is at 30 degrees Celsius, right. this is the idea of equivalent age. Equivalent age comes from this maturity method. I am saying that, so your 20 degrees Celsius concrete will take longer time to have the same maturity level, simply, right. 40 degrees Celsius concrete will get to that maturity early. How do you relate these? This relationship can be used to, so see, TETR basically is the equivalent age at reference temperature equals to this times delta T, right. Again, it is nothing but you are considering, you are using this rate relationship at two different temperatures and using that to calculate the equivalent age, because the temperature will affect the rate, right. Okay, now the important thing, how do we calculate degree of hydration, right. We all want to know what is the degree of hydration. Is it 10%, 20%, 30%, 100%, right. How do you calculate? So, this allows you to calculate that heat of hydration, because suppose you have this hydration curve, you have calculated the heat, total heat with the time, right, and I know my final HU is the total heat available from the reaction, the finally, like when the reaction completes, or you can calculate it also from your composition, because suppose you start with the cement has phase composition, you know a pure phase releases so much of heat. So, you know the heat released by pure phases, you can calculate the total heat. Also you can extend this plot for an example, right, you can extend it and get the HU value. Now, if I want to know what is the degree of hydration, simply I do HT over HU. HT I know what is the heat evolved at that particular time over HU, that gives us the heat of hydration. When HT becomes HU, what will happen? You will get heat of hydration as 1, that makes sense, right. And when your HT is equal to 0, heat of hydration is 0, that no heat has been released, that means there is no reaction, degree of hydration is 0. So, based on this curve, you can calculate degree of hydration. Suppose someone gives you the information, he say, I did this calorimetric experiment, I got this heat versus time. Can you give me the degree of hydration after 28 days? Yes, you can give. You just have to look at that curve, calculate the HU, go to the time, like suppose 28 days in this case, and then calculate this. Because heat is coming from the reaction, simply. As long as there is reaction, there is going to be heat. So, if you know the heat, you can calculate the extent of reaction. So, very important, this you will use in your homework assignment, or which we will talk tomorrow. Now, again this degree of hydration, right, can be related, right. So, this alpha, you see the degree of hydration at equivalent age, similar the concept here, degree of hydration at equivalent age can be related to alpha u equals to ultimate degree of hydration, it is an exponential function e to the power minus tau over T, right. It is again the concept of equivalent age, right. Okay, so what we are interested, right, we are looking at the sensitivity for temperature, right. These are some calculations, but we are trying to relate. So, suppose you have done experiments at one temperature, how can you translate that to different temperature, right. So, we are interested in this factor FTC, this is the A's conversion factor, which is nothing but the ratio of these rate constants at different temperatures, right. R is reference, C is suppose you use the current temperature or concrete temperature, reference is usually 20 degrees Celsius, reference 22 degrees Celsius. So, what we are saying that we are interested in this ratio of rate constants, because rate constants depend, the rate constant depends on the temperature. So, the ratio of this is nothing but the ratio of time constant, tau C over tau R, right. So, finally, we can get this relationship where we are saying that, okay, if you are not, let me just go back. So, you have this Arrhenius relationship, right, it is clear. Now, if I take log, right, what I can do? I can get, right, it is clear. So, suppose at one temperature I say K1, T1, okay. Similar thing I can write at different temperature ln K2 equals to ln A minus EA R T2, right. Now through this now I can just subtract for an example, we will cancel this out when you, and you can get a relationship between K1 K2 and your activation energy, right. Now only we want to calculate the activation energy EA, we know T1 T2, now we are interested in, so we get this ratio, suppose you subtract it, right. So ln K1 minus K2 will be K1 over K2, clear, equals to, this will get cancelled, then you have this EA over R for an example, 1 over T2 minus 1 over T1 for an example, or you can also write it minus EA over R 1 over T1 minus 1 over T2. Okay, you can try this, if you do not understand, let me know. Okay. So now we have relationship which relates the time, temperature and rates, right, K1 over K. So we are interested in this ratio K1 over K2 at two different temperatures. That is what we are getting from here. So that is what, so we have to just do, we have to calculate this ratio over Tc over Tr, what is that is through this relationship. Okay. Once you know that for a particular temperature, you can use that. So finally we can calculate this activation energy EA over R when you know Tr, Tc, Tr, Tc. It could be T1, T2 simply, simply put. If you have a data for two different temperatures, you can use this relationship to calculate the activation energy. How do you get the tau? See, you already know the temperature. How do you get the tau? You get the, through this, you calculate the degree of hydration. You have the heat, you have this plot H over T. Then you can calculate the degree of hydration alpha T. It will be similar plot. Now you fit this, you get these parameters tau and beta, right. Through this you will get tau and beta. So you know that tau and beta for a particular temperature, and you use that to calculate the activation energy. Okay. We will stop here and we will pick it up from here in the next class.